Folks, welcome to CS10 Lecture 2, everybody. Woo! All right. I am happy to say that SOPA and PIPA got killed. These are bills that were introduced to reduce online piracy. This is a big deal, folks. Those of you who are kind of following this is a really big deal. They were well-meaning bills. There is still, as I write here, there's still a tension. There really is still an issue that piracy is happening, and the goal was to try to curb online piracy. And that's a real thing, and I really support the intent of the bills, but the letter of the law was actually quite poorly scripted and could allow for a lot of censorship. So that was obviously why the folks like Google and Wikipedia and other folks stepped up and said, got to kill these bills because they are worthy of being killed. They're not written well. So maybe version 2 or version 3 would be okay, but this version 1 was terrible, and I'm glad, I personally, Dan Garcia, support that these bills went to sleep. That's great. All right. Today we're going to see and demystify. Today is one of our demystification lectures in which we're going to demystify 3D computer graphics. So it's really awesome. If you are 10 miles up in the field of computer graphics is one of the many subfields of computer science. Others are AI and human-computer interfaces and databases and computational biology. A lot of more theory. I'll talk about more of those later as the course of the semester goes on. But this is one of the biggest, and for me, it's the coolest. Why? Why? Because of images like that. Because you can do such creativity. Because of the artistic side that really can be blended with a 3D computer graphics PhD foundation. You can really have an artistic side to that. So our graphics group is ranked in the top 10. If you have any interest in this field, want to do more, there are 2 opportunities I'll talk about later. One is to do recreational graphics through a group called UC Bug. This is the local folks. And 2 is to talk to local people about some research project involving that. People often talk about 2D graphics, and 2D graphics sometimes gets confused with 3D graphics. 2D graphics is really illustration, like print media. This is really 3D graphics, which is very different. So, 3D graphics, as you probably know, is used in many different fields. You see it all the time. If you're going to watch the Super Bowl, you'll see tons of 3D graphics. If you watch any big blockbuster films, there's tons of 3D graphics involved there. One of the big ideas is that there's 2 different sides of them. There is the kind of graphics that you can lovingly take lots of time because you're going to be building up frames that end up being shown at the Super Bowl, end up being shown on a movie. And so those are kind of the film, television, and print where you might have hours per frame, where to render, which means to make the picture, to render that picture might literally take a full day for 1 frame of a 30-second film. That's a lot of time to make a 30-second short commercial. The other side is the video game market. And the video game market is one in which you have to have real-time play, in which the number of seconds per frame is not 1, not 5, not an hour, but a fraction. So you need to have 30 frames a second. So it has to be 1/30th of a second per frame. What's incredible is how much work has been done by the group of folks putting together graphics cards. Have you seen a big graphics cards in your computer? Who knows about a graphics card in your computer? Okay. So these are big cards that often cost a couple $100 that you add on to your machine. They come, most big desktop systems, for free as part of the system. And those have a rendering capability to have millions of polygons, which are little teeny triangles, per second, yielding unbelievable realism and unbelievable real-time visualization of images. So you see the picture from Gran Turismo, which is a gorgeous picture of this photoreal video game in which you're seeing 30 frames happening a second. Contrasting that with Avatar, which might have been 30 hours per frame. So there really are 2 different worlds in terms of the lovingly taking care of, I don't care how long it takes, just give me the most beautiful photorealistic image you can, or if in the Pixar sense, in the DreamWorks sense, which isn't doing kind of a plate matching, but just give me the best looking image you can. You're not doing photorealism, you're doing something else, like a caricature character. Versus the video game industry, which is give me the best you can do. I don't care if you cheat physics at all. I don't care if you cheat anything. Just give me a hack so that you can get that great performance for that game. Okay? It might not be photorealistic, but it works and it's fast. However, the line is often blurred between video games and film, and this is a competition called Scene from a Movie, in which people try to take a real movie and make a real-time video game that looks as good as that. And so this is a scene from Blade Runner. Who's ever seen Blade Runner? Blade Runner is an incredible game, incredible movie, science fiction movie, I think in the 80s. I love 80s. Give some nod. Before you were born, I think, most of you. And in which there's this rain scene, and it's incredible, and this is a real-time video game experience. So people spend a lot of time trying to do that, try to kind of blend the two. So they are blended in terms of getting movie performance, movie quality in a real-time setting. It's quite impressive, all the people who are building graphics cards, what they can do. Okay. This is what we call the 3D graphics or 3D animation pipeline. It is a 4-stage pipeline, simplified into CS10 terms. It is a 4-stage pipeline in which you have modeling and animation, and then lighting and shading where you're adding lights to this, and then you have the rendering stage. And each of those 4 pieces I'll now talk about in a second. Okay? So this is the 4-stage animation pipeline. So modeling. And modeling, by the way, if you ever see on the slide a picture of a movie, it's time for a little movie. So we're going to do a lot of that today, hopefully. So modeling means you need to model what the geometry of the world is for the system. And so that could come from several sources. That could come from, as the slide says, that could come from scanners, which are scanning something like a laser range scanner, very much what happens in a Kinect. You can have the Kinect actually feeding a geometry modeling system that could actually, you put your hands out there and all of a sudden get all the fingers in the body. A Kinect could do that work for you. That's a 3D scanner. Interactive modeling, which is actually having an animator go and move the pieces. We'll show you that. Libraries of people who have built a lot of these objects that you're just downloading, like clip art, but for 3D. Also procedural techniques, where you write a program to generate geometry. And that's really rich and really powerful. And that image you see of the Menger cube is actually that case of procedural geometry. People wrote code to generate that beautiful cube. Isn't that amazing? This also involves, and this is the part of modeling, this also involves something called rigging. So I don't usually say list rigging, but it also involves the rigging part of it, which is attaching a skeleton to whatever you build, so that when I move the skeleton, the whole thing will move around. Does that make sense? It's kind of like attaching connections to where the joints would be in me. If you're building me, you might model me, but if you don't rig me, I'm just still motionless. You have to then rig it to add that. So rigging is part of modeling here. See, I didn't say rigging, so write this down because rigging is on the slide. The key is there's a lot of math behind this. So if you like math and you like thinking about models, wow, that's really fun, you may think of going into modeling, okay? So now let's go to a film and show you some examples of what modeling could be. All right. So I showed you that video because A, it's a fun video and it expresses why animation and computer graphics is so wonderful, but also because it highlighted some of the tools that actual modelers are using. One of the tools took a couple vertices and merged them into one. That's a tool that we use in Maya, or in modeling software. There's a tool that grabbed one of the polygon faces and extruded it out. That's another tool they use. At the last step, there was she becomes smooth, and that's using subdivision surfaces based on a polygonal model. So those are the kind of tools that people use in the modeling process, in addition to kind of entertaining you for a while. So that's modeling. The next field is animation, and animation is huge. Animation is where a lot of wonderful traditional artists have found their home in that pipeline. You might have more technical folks working the lighting end, working the rigging end, but the artists, the real folks who are the deep right-brain people, have found a wonderful home in animation. And that is really where things come to life. That really is where the bang for the buck would come. If I'm Pixar, I'd put a lot of money into making sure my animators are amazing, because that's where the things come for life. The idea of animating is to bring something to life. That's the definition of animation. So that can come from someone interactively keyframing a position where they move a 3D object that's rigged nicely like this, and then take a snapshot, and then like this, and the computer will go zzz between those two frames. So the computer can automatically interpolate, write that one down, interpolate between two key poses done by interactive techniques. You could also have procedural motion. You could have maybe some flat plane move like a wave, move like an ocean. And oceans, you don't want to have an artist hand animate an ocean. That would be done based on some kind of wave technique with maybe different octaves of motion with big waves and small waves all combined together. That's actually how they do oceans. And that would be procedural motion. You also have motion capture as an idea. And motion capture, you may have seen the making of Lord of the Rings, the making of Avatar. Some of those films are used for that. And I have a little bit of a clip for that, and I'll show that right now.
What are you saying, Jake? You knew this would happen?
Because of the nature of this film, with this alien clan, this alien culture, we had a choice. We could do it with makeup, like it's always been done, rubber appliance makeup. It would have looked horrible, and it would have been boring and stupid, and kind of blue actors running around in the rainforest in their underwear, and a bunch of blue body paint. It would have looked terrible. And I wasn't interested in that. If I was going to do this, I wanted to do it this way, which is with performance capture.
But before he could do that, Cameron first had to make sure his technology could cross what's known in robotics and animation as the uncanny valley.
Let's say this is an absolute human, and this is a, kind of a talking moose. As you approach human, our attraction to the character goes down. And then at the last second, just when you get to a true human look, it goes back up. Well, we needed to get on the far side of that dip in the response curve, which is called the uncanny valley. And we needed to get to the opposite side, where we believed, we don't have to necessarily believe that it's 100% photoreal, and we don't have to necessarily believe that they actually exist, but we have to believe in them as emotional creatures. And so we came up with the head rig. We call it the head rig. It's basically just a kind of helmet, very tight conformal kind of skull cap that's based on a life cast of the actor's head and a laser scan. So it fits very tightly and smoothly and comfortably. And then, there's a carbon fiber boom that comes out with a little camera on the front of it. And that camera shoots the face in a nulled out close-up. So even though the actor's moving all around, running, jumping, yelling, screaming, jumping off stuff, jumping over logs, running flat out, whatever, we're getting that facial performance absolutely locked off.
And from that, they were able to record every facial movement, from the actor's lips to their eyes.
And that proved to exactly be the kind of holy grail approach to how to do CG faces, not the stuff that they'd done before, which is what we call marker-based. We're now image-based. We got the best animators in the world to take all this data that was coming out of our performance captures, and then we limited their options to things that were value added, like the ears and the tails. So they took a human performance with no diminishment whatsoever, and then added to it. So when people ask me, sort of what percentage of the actor's performance came through in the final character, I say 110%, because you actually had an increase in the sense of whatever the emotionality of the moment was.
For Discovery News, I'm Jorge Ribas.
So that was a great explanation of how they're adding the artistic side, which was just to add on the tails and the ears, which didn't appear in the actual facial data that came through, to climb that uncanny valley. If you've watched other videos, other early attempts at motion capture, Lord of the Rings was quite good, but some that were quite bad might be Polar Express, where kind of the face kind of floats and the eyes kind of float. People have basically said that one falls right in the bottom of the uncanny valley. Me and many other folks have said that. But Avatar climbed that edge, and it was a great description by James Cameron of that uncanny valley and actually getting above that and getting much more, the connection with the audience is much, much stronger with that. You could also generate animation through physics, but real-time physics. I might, if I want to have a waterfall, I might have water simulation and say go, and water starts flowing and water just comes, and physics just determines how things move, as well as evolution and rule systems. And I'll show you some of that in a second. Emotions are really conveyed, and this is the critical piece of the animation piece, is you have to take it from the heart. In some sense, the heart of the author initially says, I want the audience to feel this emotion, through the images into the heart of the audience. And making that connection is the difficult part. Procedural-based motion, which I think is some of the coolest work in procedural motion you'll ever see. So here is Brian Murtick, who was a PhD along with me at Berkeley at the same time. We were friends, and he had a thesis called Impulse, in which he tried to build a very physically realistic system. But to show his system off, what he did was he showed this wonderful little cart that kind of used a rule-based system. When I say rules, it followed this very simple logic you see in the right part of the slide, in which it is basically saying, well, if the goal of the cart is to push these little weevils off the edge of this little square floating in space. And it says, if I see a weevil in front of me, go forward at him. If he's behind me, then turn around and try to turn until I see one in front of me. Keep doing that, okay? If I happen to be rolled above him, then back off and do this. Very, very simple logic, okay, used for that. And it's rule-driven motion. Look at the amazing animation he gets without scripting what these actors are going to do. He just put those rules together. All they did was build that 5-node example. Looks like a baseball diamond. That's all they did with these arrows of what to do. And watch the video that results from that. Okay, and I'll narrate on top. Okay. So what you're seeing is the cart finds one of the weevils and rolls toward it, and it's now to the side. And the weevil tips over, and each weevil has its own logic. Up, and he pushes it off, and the weevil now falls into I call it the vat of food. Think of it, it's not being killed, but it's actually being sent to where the food is. And so I'm just trying to spin it positively. So it turns, now it's on top of it, it's kind of trapping it, and his system was quite impressive to handle all the physics of those interactions. It now backs up, and now it zooms forward, and he's trying to run away, it's so sad, and he pushes it, and it falls off on its own. It spins its wheels. All of this was automatic. He never once said, turn right, turn left, go forward, go back. Those 5 nodes created all that animation. It's pretty incredible stuff. And again, he's kind of trapping it. And his system was actually, for the time, for 96, it was quite impressive on all of the interactions and how it did it really right to handle the friction of the wheels. What happens if a virtual mass of the wheel, of the virtual mass of the cart, and all the other guy. And the other guys now were going, run away, run away. And the wheels are kind of wobbly, and he backs up, tips it. Watch how it backs up and tips. All of that is really wonderful motion and a testament to his system in terms of the realism of the emotion, of the motion. But I'm saying the testament is in those 5 simple node states, he almost pushed himself off. In the 5 simple node states, he was able to create incredible motion. So that's procedurally driven or rule-driven motion. Quite impressive. Lights, do it. All right. So what I haven't shown you is genetic algorithms. And genetic algorithms are another incredibly powerful, incredibly exciting field of animation. Automatic animation. Here's the idea. Ready? I'm going to breed these robots in the system. And they're going to breed based on if they win kind of Olympic challenges like swimming fast or getting to a particular node. And as the winners win, they get to breed and have mutations of themselves. And all their children now compete in the Olympics. You get this? So they keep competing in the Olympics, and those winners get to make other children. It's kind of like the survival of the fittest, if you will. But virtually, okay? These are called the genetic algorithms. This is Carl Sims' work from 1994. We're edging on a 20-year anniversary. And even today, it's incredible, incredible work. So let me show you some of Carl Sims' work. It's called Evolved Virtual Creatures. Let's see if this one can work here. Come on.
This demonstration shows virtual creatures that were evolved to perform specific tasks in simulated physical environments. Swimming speed was used to determine survival. Most of the creatures are results from independent evolutions. Some developed strategies similar to those in real life. Once they're evolved, multiple copies of these creatures can be made and simulated together in the same environment. The next group of creatures were evolved for their ability to move on a simulated land environment with gravity and friction. Some simple solutions with just 2 parts were found. Some seemed like they could use some assistance, while others were fairly efficient, such as this rowing-like behavior. Here is an odd cousin of the previous. A mutation caused him to tumble. Some creatures evolved to incorporate contact sensors in their control systems. Here is another inchworm-like creature that tends to go in circles. This was actually a creature first evolved for its ability to swim in water, then later put on land and evolved further. A successful sidewinding ability resulted. Here is one with a hopping style. The protrusions on its arms seemed to help prevent it from tipping over. This was the fastest, with a successful galloping-like stride. This group was evolved for their jumping ability. This group was evolved for their ability to adaptively follow a red light source. The resulting creatures are now being interacted with. A user is moving the light source around as the creature behaves. This one seems to flail randomly, but somehow still manages to approach the light. Perhaps it is mean to move the goal away just as it arrives. Here is one that has propeller-like fins which are tilted depending on the direction of the light. It can adaptively swim up or down very well. This final group of creatures was evolved for their ability to compete for control of a green cube. The creature closest to the cube at the end of a simulation is the winner. Here, a strategy first arose for simply tumbling towards the cube. Then one learned to block out his opponent. But then later one learned to overcome the obstacle by climbing over it. Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube. The success of a strategy is often highly dependent on the opponent. Here is a hockey-playing creature, which takes the cube away and wins by a large margin. Here are 2 similar hockey strategies battling it out, with appropriate gestures. This crab-like creature walks well, but often continues past the cube and instead seems to prefer beating up on his opponent. Against the arm, the crab seems to simply walk away. A successful strategy is this 2-arm technique that swipes quickly in from the side and moves the cube over to a second arm. These are the final rounds of competition amongst the overall best. Finally, the seeker arm goes against the side swiper, but the cube is just out of reach.
Awesome stuff, right? 20 years old is that work. Incredible. All right, so that was genetic algorithms to the line of automatic animation. Nowhere did he say move this way. He just set up a system where genetically it would evolve with a control system to animate and do the right thing to try to achieve those goals and those Olympic tasks. So that was the first 2. That's modeling and animation. Now we're up to lighting and shading, the 3rd stage. And this is just like a movie. So if anybody's worked in film before, if you've ever worked in film at home, this is the virtual thing. What we do is exactly like you do in real film. You set up a camera, we set up a virtual camera. You set up lights, we set up virtual lights. It's exactly the same thing. The lights can be area light sources, like the light sources in many classrooms, or they can be point light sources like a very bright LED, or it can be a long directional light source like the sun. You can have all these things in the virtual side as you have the creativity you do in the real side. Teams of artists also apply things called shaders. And shaders are the things that make things have anything more than a gray plastic shading to them, look to them. If the computer goes by default, it will give everything a gray plastic look. But every time you see an amazing photograph, as I show in these slides, an amazing image, a computer graphics image, a CG image, you're seeing leaf texture, and you're seeing banana skin, and human skin, and hair, and shirt texture, and different kinds of shirt, shiny versus rough. All of those things are things that people can program. You actually, rather than, you say, oh, that's easy. Then you take a picture of a leaf, and that's what it is. That's what they did 20 years ago. Now they're actually coming up with procedurally done shaders that involve a lot of programming to get the look of an exact leaf. The layers of it, the many different layers of how light's bouncing around is quite complex, and programmers are now writing shaders, which is quite incredible. At the end, rather than saying action, you say render. Render just means make the picture, rather than action, which means you're capturing on film. How does rendering work? This is the hardest part, probably, of the slides. Everything so far wasn't really hard for you. This is the only math we have in the slide. And here what I'm showing you is similar triangles. The eye is in the bottom of the screen, of the image. That horizontal line is the image plane. That blue square is a cube out in the world. And what do you draw on the screen? What do you draw on that image plane is basically coming from a very simple set of equations, which are similar triangles. The ratio of the x distance from the eye to where it hits on the image plane, the little x, the little yellow x, over the x distance from the eye to the actual cube is equal to the y distance from the eye to the image plane, which is known, over the y distance from the eye to the actual cube. You get that? So you know all the values, and you're trying to solve for where that x distance is. Does that make sense? Because you know where the cube is in 3 dimensions. That's easy. And you know where the image plane is. So you know what that height is. But you don't know where the x is. That one, the x value. It's called b of x in this equation. And you're just trying to solve for b of x, which is b of z times a of x over a of z. It's literally, that's all the mathematics that's really going on at the deepest level of a graphics card to generate pictures on the display. Isn't that cool? And in fact, I have a demo, if I can squeeze it here, to show it to you. Look at this guy. It's called ppcabinet.rot. There's a software lights called Rotator, which is going to show you, this is an image of, there's a cube. Look at this, 3 dimensions. See that cube in 3 dimensions? I'm going to spin it. There's a cube in 3 dimensions, and it projects through those lines. See, those blue lines are my projection lines. And you end up getting that green picture on the image plane. See how that works? Don't worry about the math. The math is just so similar triangles. But essentially, I take all the corner points, and I draw lines as if the lines are pointing towards the sun. That's like the reverse picture. Or towards the viewer, actually. Okay? So I'm now the viewer. All the lines, when those blue lines line up like this, guess what? That's the picture you get. See, because that's the view you get from the eye infinitely far away. This is called parallel projection, and it makes the math is a little easier than perspective projection. But thinking of me of being infinitely far away, watch that. That's exactly the picture, because that's why you get it. See? You just draw the corner points from all the corner points of the cube through that purple plane, giving you that green projection. Isn't that cool? That's all it is. That's the math. If you all said, how does that stuff work? That's the picture. That's how it works. It's pretty cool. All right, back to lights and back to the video. All right, so that is projection, and that is the rendering process and how the math of projection actually works. There's lots of algorithms to do this, and what we use as a metric is what we call the cost. If I said, oh, you can't use that algorithm because it's too expensive, does that mean the licensing cost? No, it means how much time it will take to generate the picture. If it might take a full day, and that says I can't do it because I have a deadline to produce the movie by some time. So I can't use the algorithm that's so remarkably photorealistic, but it's going to take a full day per frame, and if I work out how many frames I need, I can't make my deadline. So when I say expensive in this context, it means it takes too long. Okay? So there is another important thing you understand, which is global illumination. And global illumination is in a rendering model. Once you're trying to do the algorithm for rendering, you don't even know what an algorithm is yet. You'll see that pretty soon. But in the process of making the picture, people now realize that global illumination, which means trying to simulate where all the photons of a scene are actually bouncing and landing, that's the right way to do it. If you don't use global illumination, you'll see the results. And those are called direct illumination. If you use a non-global illumination renderer, it's called direct illumination and not as good. Let's look at a picture. One of the ways you measure not as good is something called the Cornell box. And the Cornell box is, let's take an actual photograph and let's take a rendering. Meaning we have a virtual cube and a virtual big rectangular solid and a virtual green wall and a virtual red wall. And let's take an actual green wall and an actual red wall. And let's see if our image, our rendering, our computer graphics simulation of that is close to the real thing. That's a really important idea. How do you know whether you're good enough? The people at Cornell, building the Cornell box, says we won't know until we have the real thing and we have our simulation and we compare those and see if those match up exactly pixel for pixel. And they did, and it was incredible. So that said a lot about the quality of their rendering algorithm being photorealistic. And that was very important to be able to close the loop in terms of getting the feedback of whether something actually works or not. This is a direct illumination image. And take a look at that and see what it looks like. And you say, oh, that's pretty good, right? That's a mirrored ball and a glass ball. But you're thinking, wait, light doesn't work like that. That glass ball has no light going through it because the rendering model can't support that. Watch this. Bam. Look at that quality. You get a caustic where the light goes through the glass ball and forms a highlight like a magnifying glass. You get real lighting effects. And so by having a global illumination model, you get much better to photorealism than a bad direct illumination model. But you don't get something for free. It costs more. And what costs means it takes more time, okay, to simulate all the photons in the scene. So if you're interested in this, the way you learn more is something called UC Bug. UC Bug is an undergraduate group in computer graphics, and I will take you from zero, from Jump Street, from never seeing computer graphics, never knowing anything more than CS10, to making a short, an animated short film. And this is a class taught by students as a local decal. I want to encourage you all to think about that. CS124 is also a course here at Berkeley about graphics. In summary, I can't think of anything that summarizes the beauty and joy of computing more than 3D computer graphics. And being able to share with you, kind of lifting the hood and explaining that to you has been really a privilege for me because I love this stuff. I've been doing it for the last 20 years. I love it. It has transformed film, print, video, YouTube. It's been transformative in terms of being able to have simulations and robots taking over the world. All those, the imagination of artists and film artists have really exploded thanks to the advent of really high successful 3D computer graphics. There are 4 stages: modeling, animation, which is also rigging, lighting and shading, and rendering, and it allows people to exercise the right side of their brain. 3:59, I just ended on time. Thanks, folks. That's end of the class 2. We'll start again on Wednesday talking about video games. All right.